So let's continue with this chapter 5, which is single phase or ideal gases. And we are going to check this, which is liquid hydrazine. They give you this specific gravity, undergoes a familiar decomposition reaction that can be represented by this expression. And this is very funny because you have X's in these stoichiometric values. Okay, but essentially it's N2H4 goes to hydrogen gas, nitrogen gas, and ammonia gas. The first thing they tell you is for what range of values of X is this equation physically meaningful. So yeah, of course, mathematically makes a lot of sense, but physically or chemically, when is it meaningful? So I'm going to use the stoichiometric coefficients. You know, by definition, they cannot be zero. So I'm going to take this 6x must be bigger than 0. This 1 plus 2x must be also bigger than 0. And this 4 minus 4x must be bigger than 0. So let me this is just math. This is x must be minus 1/2 and x must be 1. Essentially, this is kind of tricky. Don't forget that when you have inequalities, you gotta change when you translate this one to here. So yeah, we have these ranges. X must be bigger than 0. X must be bigger than minus 1/2. Here 0. And x must be less than 1. So we have 1. So we have this here value and this here value. Which one to choose? And yeah, you don't need to do math here, but you know that by math you cannot choose this here because they tell you at this here that it must be bigger than 0 and less than 1. So I'm going to choose this value, but only, guys, let me tell you that if you use minus 1/2, you will see that it is not possible for this 6x. Because 6x, if you use minus 1/2, this is negative, you will get minus 3. And maybe for this is okay and for this is okay, but for this 6x is not okay. Minus 3, you cannot have negative coefficients, so I'm not going to choose that. And yeah, they tell you you can use 0, but essentially you cannot, because you cannot have the 0. So I'm not going to include 0. I'm going to include 1. Yeah, yes I will. Because actually, no, you cannot also, you should never include 1 also, because for this you have 1 minus 4 times 1, you will get 0, which is also not valid. So please do not include these values here. This is a range. Now they tell you letter B, plot the volume of product gas at these conditions, pressure and temperature, that will be formed when 50 liters of liquid hydrazine turn into hydrogen, nitrogen, and ammonia gas. So we have the specific gravity, that's good, specific gravity, 82 grams per milliliter, and we have 50 liters. So 50 liters, the mass will be, mass of liquid hydrazine will be 50 liters of liquid hydrazine times 82 grams divided by milliliter, and we know 1000 milliliters, it's 1 liter. So the mass will be, let me calculate it, 50 times 0.82 times 1000. It's about 41,000 grams. Or let's change these 2 moles of liquid hydrazine, just the mass divided by the molecular weight. The molecular weight, how much is it? It's 32 grams per gram mole. We have 41,000. Let me use kilograms. This is 41 kilo. And this is kilogram per kilo mole. So you got 1.28 kilomole of liquid hydrazine. Why moles? Yeah, because we're going to use moles to relate to stoichiometry. So let me check this value. Moles of product will be this 1.28, or the initial moles in reactant, times the relationship. So for every 3 you got 6x. Let me write this here. 3 moles to 6x, 3 to 1 plus 2x, and 3 to 4 minus 4x. So just write this relationship. You got 6x of hydrogen per 3 of hydrazine, liquid hydrazine, plus 1 plus 2x nitrogen. Yeah, I think it's nitrogen. Yeah, nitrogen, divided by 3 moles of liquid hydrogen, plus finally 4 minus 4x of ammonia gas, I think NH3, by 3 moles of liquid hydrogen. So we got our expression. What we're going to do is to simplify this mathematically. You should get, and I'm going to do this, but you can take out these 3, it's the same 3, so I take it out and I got 6x plus 1 plus 2x plus 4 minus 4x. And eventually you get to 0.426 times 4x plus 5. Doing more numbers, 1.7x plus 2.13. So this is your expression for moles in product. So they tell you in Excel, I'm going to bring you in Excel here, but in Excel, model for PV equals nRT, we will calculate volume, which is essentially nRT divided by pressure. Let me just, the thing we're going to do in Excel, just give me 1 second. It's moles, you don't know how, and P, you don't know how much. We're going to use X, this is a function of X, times the R, which is H.314, times the temperature, which is 80 times this, and the pressure, which is 10 to the 6 pascals. So yeah, we are going to essentially do a table in which we include X. We're going to give values of X from 0 to 1, and we are going to calculate the products because we have this in X function. And with this, we're going to calculate the volume, which is a function of NP. So see you in some seconds. So welcome back, guys. I've just calculated everything here. I just gave values for X. Look for, since we know X is limited by 0 to 1, I use 0, which actually this is not, you shouldn't use 0, but I use just as a reference. I have NP as a function of X, which is 1.7 times X, which is here, plus 2.13. So I got this, everything here. This is the amount of moles in the product. So this is the amount of moles in the product, which are essentially gas moles. And then I calculated the volume with B equals nRT divided by P. Let me do this. First, the total amount of moles, which is this blue cell, then times R, which is constant. That's why I have this as constant. Times 600 times plus 273, which will give me the absolute temperature, divided by the 10 bars. I changed them to pascals. So I do everything here, guys, and yeah, essentially I got the volume in this exact same volume. I get it to liters, so you can have a little bit more like tangible results. So as you see, as X approaches 1, it goes rapidly to 2.8. So that's the conclusion. The conclusion will be, yeah, let me just go to the spreadsheet before, and let's conclude. We're once again here, guys. Let me just, they tell you, okay, plot, we already plotted, and yeah, speculate on what makes hydrogen a good propellant. The thing here is a propellant is usually propellant used for I don't know, you have a small thing here, let's say it's a rocket. Propellant is used to move the rocket. So I think it's very, very good, because for each 3 moles of liquid hydrazine, which does not occupy that much space, actually specific gravity is it's 82% from that of water. So we got, I don't know, let's say 1 liter. It will be a little bit more, let me just check here. Let's use actual values. If we got 1.28 kilomole, 1.28 kilomole of liquid hydrazine, this will give me a lot of, where is it? Okay, 41 grams, okay. This will give me a lot of space, because I will generate 3 mole of hydrogen. Where is it? Yeah, 3 moles of hydrogen. X. Let's use X as 0.99, which in the table will be something about 1. So this here will give me the maximum amount of moles. So 1.7 plus 2.13, which is this here. And let's go to the Excel here. Yeah, we got this. You got a lot of volume just for this amount of moles. So what you want to do is to have the least amount of moles in liquid, so you can transport them easily, but when reacted to have a huge volume so they can propel the rocket. So that's everything, guys. Just very, very easy. Let me give you a small conclusion. Why I use these values is mathematically. You know that this here must be bigger than 0, actually bigger than 0. So you get X must be bigger than 0. And then you use the same logic here and the same logic here. Eventually you get to the conclusion that X must be between 0 and 1. And then using specific gravity, we calculate the amount of moles in the liquid hydrazine. And then we pass to here, which is essentially the amount of moles by X, or a function of X. And we calculated the X, well, we gave some values. We know X is from 0 to 1. And then we calculated NP and then V from NP, which is everything here. I'm going to add this Excel to the web page. So essentially, this is everything for the video. See you in the other video.